Okay, so we're going to try to wrap up the discussions, whatever we can with regards to the mathematical tools that we can use to characterize random processes, right? So the first thing that we did, for the last two classes was for the last class was to try to characterize the first order PDF or the first order PMF of a random process. Recall that a random process sampled at any particular time t or a discrete time n is nothing but a random variable. So that could either be a continuous random variable or it could be a discrete random variable. And in order to characterize that random variable anywhere in time, we just need the first order PDF or the first order PMF. Okay. Now my question for you here is, if I give you the first order PDF of a random process, right? So for example, so this is, so as an example, the random telegraph signal that we did in quite a bit of detail, I gave you the first order PDF or first order PMF of the random process, okay? So what was that? We found out that the probability that x of t equals 0 is this equal to half plus half e raised to the power minus 2 lambda t, and the probability that x of t equals 1 is half minus half e raised to the power minus 2 lambda t. And no matter what t is, from 0 to all the way up to infinity, I can describe exactly what the PMF for this random process is going to be. Is that all that is necessary to completely characterize this random process? What do you think? Is that all that we're going to need to completely characterize a random process? I mean, or do we need other information as well? So the question once again is given the first order distributions, do we need additional information? Info to characterize a random process, right? Completely. Jimosin, what do you think?
Sir, I think we've described statistical information about the random process. We still need some temporal information about the random process.
What do you mean by temporal information?
Sort of its variance with time. Is it invariant with time? Does it vary with time? That sort of information.
But can you not extract that information from this first order PDF or the first order PMF? For example, this first order PMF, it's clearly visible that the PMF is a function of time. It does vary with time. So is that not enough to tell you the information that you just mentioned, Mohsen? या कुछ और भी चाहिए? Right. So let me then step back and talk about a simple toy problem. Let's say I give you two random variables, right? I gave you a random variable x1 and I gave you a random variable x2. And I tell you that the random variable x1 has a certain PDF and random variable 2 has a certain PDF as well. Is that enough to describe these two random variables? Or do we need something else on top of the individual PDFs? क्यों Zephyr? I have x1, random variable x1, I have random variable x2, I have the PDF of x1, I have the PDF of x2. Do I need something else?
Sir, would we need to define some range in which it is valid?
So I'm given the exact PDF of x1. I've given the exact PDF of x2. The PDF of x1 completely characterizes x1. The PDF of x2 completely characterizes x2. Is that enough to describe these two random variables, or do we need some additional information? Jigazi.
Joint PDF?
You need the joint PDF, right? You need the joint. Without the joint PDF, you don't know how x1 is dependent on x2, right? So you need that joint PDF, right? And if I gave you three random variables now, in order to describe them completely, you will need the joint PDF of the 3 random variables. Okay. Now, given this fact, are the first order PDFs enough to describe a random process? Right, and I'm nudging you towards the answer, right? I just have the first order PDF of the random process. So that means, okay, if I sample it at T1, I have the PDF for that random variable. If I sample it at T2, I have the PDF for just that random variable sampled at T2. Okay? What I don't have is what? I mean, what the first order PDF does not tell me is what? Nazish, what do you think?
The relation between the first and the second is not known for time T1 and for time T2.
Okay, good. Right. So what you need, so the answer is yes. What you need is joint PDFs. Right. So I say x1 was x of t1, right, and x2 was x of t2. So the random process sampled at time t1 is x1. The random process sampled at time 2 is x of t2. Right? In order to describe these two random variables completely, what you need is not just the first order PDF of x1 and the first order PDF of x2, but rather the second order PDF or the joint PDF of x1 and x2, right? So in order to completely characterize these, what you need is a second order PDF. And I would denote that with x1, x2 sampled at t1 and t2, right? So this is a second order distribution, if you will. Okay. So this is the second order PDF, right? So in order to completely characterize a random process now at 2 points, you actually need more than the first order PDF that I just described above, right? You need the second order PDF now. Okay, so you want to find out what is the probability that x of t1 equals 1 and x of t2 at some other time t2 is equal to 0, and for all the 4 combinations. Okay, that will completely characterize these two pairs of random variables that as a function of t1 and t2 for different t1 and t2. Okay, I say would these two be enough? I mean, would these two be enough to completely characterize a random process now? Emosen, what do you think? Or do we need something?
I think so, yes.
Yes?
I think so.
Okay. जी हाँ जी.
I think मतलब जितना मर्जी आप चलाएं चाहे आप चलाते जाएं, third, fourth, fifth आगे चलते जाओ.
Yeah. Okay. जितना मर्जी
And that would further characterize the system.
Okay. Good. Isha and Shaila?
Sir, wouldn't it depend on the fact कि जो आपका random process है वो कितने variables पर मतलब उनको कितने variables हम उसको characterize कर रहे हैं?
तो कितने variables से characterize कर सकते हैं? Why don't you tell me that?
If we're doing it with more than 2, then we would be needing.
Do you need more than 2? I mean, why would you not need more than 2? Okay, so now remember, this is a function of time. The random process is a function of time where t takes on a continuum of values from 0 to infinity in this particular case, right? So how many random variables do you have in that random process? How many random variables in that random process? There are infinitely many. As Ghazi said, ye to chalate jaye aap, right? So there are infinitely many random variables that characterize the random process. And so in order to completely characterize that random process, you need the nth order PDF or the PMF and the order distribution for all integers n, no matter where t1, t2, t3, t4, jahan marzi lene, you will need those nth order PDFs to completely characterize that random process completely. Okay? And that becomes a very, very difficult task most often, right? So typically that's a very, very hard task, because a random process is actually a signal where at any time that you sample that process, you get a random variable, and therefore the random process is made up of so many random variables that you will need to describe a very, very complex sort of function, right, for all orders, for all times, for all nth order pairs of times, where n goes from 1 all the way up to infinity. Okay? And that becomes very, very hard, right? So that's infeasible in practice most of the times, right? So therefore, on account of the difficulty that we see in completely characterizing a random process, what we end up doing for most realistic random processes, we resort to simpler yet easier to compute matrix, right? Easier to compute characterizations, which are simpler in nature, which does not completely characterize the random process, but it does tell us some information about the random process. Not complete information, but some information. Okay? And the reason why we go there, of course, is once again because they're easy to compute. And those tools or matrix are what they're listed here. They're either the mean function, the autocorrelation function, or the autocovariance function. And autocovariance function and autocorrelation functions are quite related to each other, as we're going to see, right? So the first thing we want to talk about is a mean function. And the mean function, as the label dictates, or the title dictates, is nothing but the mean, right? And why do I call it the function though? I mean, why is it not just the mean? So this is nothing but the expected value of the random process. G. Mohsin, you have an answer?
So it's a function because it varies with time.
It is a function because it may vary with time, right? Excellent, right? And here's how. So we say, Kiji, if I want to compute the mean of a random process, right? This is what I want to do. This is what I want to do. Expected value of x of t, right? This is the mean of a random process. But I know that as t varies, the random variable changes, right? So the random variable changes as a function of time. And therefore, the mean should also vary as a function of time, right? So therefore, this must be equal to something which is a function of time, right? And that's why it's called the mean function, right? Because this is a function of time now, right? So you basically, essentially what you're doing is you're saying, I am going to sample it at some time t, and we're going to see at that time t, what was the expected value or the mean value that this random process could have taken, which is essentially just the mean value of the random variable that results when you sample that random process at that particular time t. Okay, and by definition, we know what will this definition be, and let us for all of our discussions from here on, let us just only provide definition. I'm going to only provide definitions for a class of random variables which are continuous time and continuous in amplitude. Okay, so that's I'm going to stick with. So that's a disclaimer here. All of my discussions from here on and my notes here on are going to apply to a class of random variables which are continuous time and continuous amplitudes. The idea is very, very easily extendable to discrete time. Discrete time is if n ko discrete karna hai, and discrete amplitude where the PDFs are just going to be replaced with PMFs. Okay, so that's something I want to say at the beginning. Okay, so if x of t is a continuous time, continuous amplitude random process, what will this be equal to as a definition? G. Mohsin.
So the infinite integral of x multiplied by the PDF of the random process.
PDF of the random process, the first order PDF of the random process evaluated at time t.
At t.
Exactly. So this is fx. So this PDF is now, as we said, is a function of two variables, x and time t, and this integral is over x. So then at the end of the day, when you integrate over x, what you're going to end up with is a function of t. Okay. So this is the mean function. Okay. So this is a mean function, and it's a function of time, right? So that's why it's called a function. mean function. So function of time. Right? And if this was, by the way, a discrete amplitude random process, so this integral would just be replaced with a summation, as we're going to see perhaps in the next example. Okay, so let's start doing some examples here to compute the mean functions. So the first example is that random telegraph signal that we just did in the last class. Right? And the random telegraph signal, I have the first order PDF. What is that first order PDF? First order PDF says that the probability that x of t equals 1 is half minus half e raised to power minus 2 lambda t. Right? And what was the probability that x of t equals 0? Somebody? This was just
1 by 2.
1 by 2 plus half e raised to power minus 2 lambda t. Okay. Now, what is the mean function here? So by the way, what kind of a random process is this? This random process is continuous time, and what about the amplitude? What about the amplitude? Dimosen?
Discrete.
Amplitude is discrete, right? So this is mu x of t is, which is the expected value of x of t. And since this is discrete, so this is just 1 times probability that x of t equals 1 plus 0 times the probability that x of t equals 0, right? And clearly this must be equal to half minus half e raised to power minus 2 lambda t, right? And we clearly see that the mean is now clearly a function of time. As time increases, or as time, when time t equals 0, the mean is what? When time t equals 0, the mean is? Jigazi?
0.
0, right? And as time t increases, the mean starts increasing and saturates to half. Okay, and that's where 1 and 0 actually become equally likely, and that's why it saturates to half. Okay, so the mean in this case, the mean function is given by this expression for the random telegraph signal. Let me do another example here, which is meant to illustrate a point. And this example, let's say the random process was given as x of t equals a times sine omega naught t, where omega naught is fixed or deterministic, and a is a uniform random variable between 0 and 1. So this is one of the examples that we did earlier as well. Okay, and you're required to find the mean function of this. Now, the point I want to make here is that in order to find the mean function, you do not necessarily need to compute the first order PDF or the first order PMF of the random process. Okay, you can do it without that, as we're going to see in this example. So the mu x of t is just simply expected value of x of t. That's the definition of the mean function. And this is equal to expected value of a times sine omega naught t, right? So what is this equal to? Dimosen?
So 1 by 2 sine omega naught t.
Yes, so this is equal to expected value of a times sine omega naught t, because as far as sine omega naught t is concerned, that is not random, that is deterministic for any fixed time t. Okay, so therefore this is just equal to half. The average value of a is half. This is half times sine omega naught t. Okay, let's do another example. And this example, x of t is equal to a, which is a constant, sine omega naught t, when omega naught is a constant, plus theta, right? So here A and omega naught are constants, and theta is uniform between 0 and 2 pi, right? So theta is uniform random variable which can take on any value between 0 and 2 pi. So what is the expected value of x of t, or the mean function, if you will? Me x of t is expected value of x of t. So this is expected value of A sine omega naught t plus theta, right? So how do I compute this? Isha?
Sir, we have a constant being multiplied, so we could perhaps take it out
Okay.
and be left with the expectation of sine omega naught t plus theta, which would be the same
What do you
as
mean?
that was for sine omega naught t.
Why?
Because sine is a periodic function.
So
So if we have theta added to it,
yeah,
which is from 0 to 2 pi,
yeah.
we would have the same value as it would have been before it was added.
Theta is random.
Oh, right. Yeah. Sorry. So sin alpha plus beta की property लगा सकते हैं शायद.
जी मोहसिन?
सर क्योंकि यहाँ पे थीटा रैंडम वेरिएबल है तो आप इंटीग्रल विद रिस्पेक्ट टू थीटा ले लें.
Excellent, right? So this is basic chapter 2 stuff. Right? So this is A, and I am going to integrate with respect to theta, because what I have inside the expectation is a function of the random variable, which is theta. And the PDF of theta is what? Is just 1 upon 2 pi, right? So this I'm going to integrate over 0 to 2 pi. Integrate what? This is sine omega naught t plus theta times the PDF of theta, which is just equal to 1 upon 2 pi d theta. What is this equal to? Shoaib, what is this equal to? Okay. Anybody else? Zephyr, what do you think it's equal to? I mean, you could go ahead and compute the integral if you want to, like, you shouldn't really do it. I mean, this is, should be clear.
Cos omega naught t over omega naught. I mean,
okay, G Mohsin?
सर पीरियोडिक फंक्शन है.
Yeah.
Between 0 and 2 pi, तो वो 0 हो जाता है average.
Right, so this is 0. I mean, I know that the area under the curve is under a sinusoid over one period is 0. Right, so it's a sinusoid is a function of theta, and so the area under the curve is 0 for a sinusoid. Okay. Okay. All right. Okay, now I'm going to move on to, so from the mean function, I want to go a step further, right? So the mean function basically is, you can say, yeah, this is a sort of a first order characterization. I mean, for this, you don't really need, so all this tells you, I mean, it does not tell you the first order PDF. So it's information that is slightly less than the first order PDF, right? But it tells you, okay, what the mean value of the random variable, random process is going to be as a function of time. Okay, so that's the first order characteristics. Right? Second order characteristics, on the other hand, just like for random, for pairs of random variables, we define something called the correlation between two random variables. Just like that, we can have a correlation function characterizing the second order characteristics of a random process as well. Okay, so this is, so next topic is correlation functions, the autocorrelation function, in fact, the autocorrelation function. And the definition for the autocorrelation function is the following. Rx and is defined at T1 and T2 is a function of two time indices, T1 and T2, and is defined as the expected value of x of T1 times x of T2, right? So if you just try to link this with our discussion earlier on pairs of random variables, what the autocorrelation function tells you is this autocorrelation function evaluated at T1 and T2 is actually the correlation between two random variables. And what are those random variables? Those two random variables are x of T1 and x of T2. Okay? And as I change T1 and T2, right, my random variables x of T1 and x of T2 change as well. So therefore the correlation between these pairs is going to change as well. That's why it's a function of two time indices, T1 and T2. Okay? And based on the definition, so what we'll need here, so this is actually a two-dimensional integral. So this is x1, x2. And what I am going to have here is the second order PDF of the random process, x1, x2 evaluated at T1 and T2, and dx1, dx2, which we often do not need to go into. Often things are much easier, okay, as we're going to see in the next example. So for the example, I'm going to go back to same x of t equals a sine omega naught t plus theta, right? So I have already computed the mean function, right? So I have already computed the mean function for this example up above, and we found out that the mean function is equal to 0, right? No matter where you sample this random process, the average value at that point in time is always going to be 0, okay? What we're going to do next is, okay, we want to find the correlation function at some time T1 and at some time T2, okay? So I'll just apply the definition, and the definition just says that evaluated at T1 and at T2, the autocorrelation function evaluated at T1, T2 is just simply equal to expected value of x of T1 times x of T2, which is equal to what? Which is equal to expected value of a squared sine omega naught T1 plus theta times sine omega naught T2 plus theta. Okay. So remember, this theta in both is the same because there's the same random variable that characterizes the entire random process. It's one random variable that characterizes the random process. Okay. But the times are different, right? So this actually corresponds to x of T1, and this somehow corresponds to x of T2, right? Without the a actually. Okay, how do I evaluate this now, the expected value? How do I value this expected value? Okay, so I'm going to use trigonometric identities here, right? So sine A times sine B is equal to half cosine A minus B minus half cosine A plus B. Okay, so that's something I'm going to use, and for that, this is going to be a squared by 2, and this is expected value of sine. The arguments, I'm going to subtract them, so actually this is cosine. So this is cosine. The arguments, you subtract them, and what you're going to get is omega naught T2 minus T1 and minus cosine, and this is going to be both of them added up, right? So this is omega naught T1 plus omega naught T2 plus 2 theta. Okay. So what is this expected value? Geozephas, I'm going to come back to you. So what is this expected value? So expectation is over theta. Remember this, the randomness is in theta.
So if we take the integral as we did earlier, then the term involving cos omega naught T1 plus omega naught T2 plus 2 theta, that is gonna go to 0.
Yes.
And
what about the first term?
That's like a constant, so
Excellent.
we're just gonna multiply 2 pi with it.
No. Why?
2.
So what is the expected value of a constant?
Oh, it's the constant itself.
It's the constant itself, right? So this is just
okay.
cosine omega naught times T2 minus T1. Right?
Sir, with regards to the example that we did earlier with the same thing, I was just confused. How is like the mean value coming out to be 0 if we fix the time? Like usually when we take a sinusoidal signal and integrate it over its time period, then it comes out to be 0. But in this case, we fix the time. So
yeah, but so the integration is over theta, not over time. So you fix the time, that I agree. So as far as that omega naught t is concerned, omega naught t is really a constant because time is fixed. And it's actually the theta that can vary from 0 to 2 pi randomly, anywhere.
Oh, okay.
Okay, so this is what you're integrating, right? So you're integrating over theta and not over time. Time is fixed. That I agree with you.
Okay, sir.
Like, and so what we have on the x-axis is a function of on the x-axis is theta, and on the y-axis is sine side as a function of theta. And that area under the that curve is 0.
Oh,
Time
okay.
is fixed. That I agree.
Understood.
So एक constant phase add करता है वो सिर्फ.
Oh, okay, sir. Thank you.
Okay. And the similar thing applies here as well because it's cosine omega naught T1 plus omega naught T2 plus 2 theta. So it's actually just a compressed sinusoid, right? So it's compressed by a factor of 2, and so it's just a period pi hai, and integrating over 2 pi once again is equal to 0. Okay, so this is what you get: is a squared by 2 times cosine omega naught T2 minus T1, right? And in this particular case, what we observe is that the correlation function or the autocorrelation function turns out to be a function of the difference between time T2 and T1. It's not a function of T1 and T2 separately, but rather only the difference between the two. Okay? And that's why oftentimes we also use this notation to represent the autocorrelation function, which is this is our x T1 and T2. I mean, this is what we started out with. So often what we use is indicating that it's a function of t and time t plus tau, right? So this is just describing it a little differently. In the sense that you were describing it as a function of some time t, and then the separation between the two time instances. Okay, so that's just a sort of a different interpretation, right? Yeah, if I fixed my time t1 to t, right, and then just want to see kg, what happens if as a function of the separation between t1 and t2, where that separation is actually tau now. Okay, so I describe this now as a function of some time t and a difference of this time with the next time instance. Okay, so that's an equivalent representation. Okay, so here if you equate the two, basically t2 minus t1 is actually tau, right? So where tau is the separation between the two time instances. Okay, And it turns out what we have up above in this example, the autocorrelation function, that's a function of the difference between T2 and T1. It's not a function of T1 and T2 individually. Okay, so that's going to come up later as well. Okay. All right. Let's do one more example before we take a break. So what we have here is let me write it out. This is a function of T2 minus T1 only, right? And not a function of T1 and T2 separately. Okay. All right. Let's do one example. So there's another example. And this is actually an example that we've done. So we're going to assume that W1, W2, all the way up to infinity are IID Gaussian. So Wi are really Gaussian zero mean and variance sigma squared. Okay, and the process is defined as follows. The process is described as an accumulator process, right? So x of n equals x of n minus 1 plus w of n, right? Where for all n equals 1 to all the way up to infinity, and the additional information is that the initial starting point is 0, right? X of 0 is 0, right? So the initial conditions are 0. Okay. Now, based on this, we were able to say something about this process, which actually since this is an accumulator process, since this is an accumulator, right? I can conclude that x of n must be equal to summation from I equals 1 to n minus, actually, I equals 1 to n of wi, right? So this is actually a sum of Gaussian processes. Gaussian random variables, okay, and Gaussian random variables. So by the way, what category of the random process does this relate to? This is a discrete time random process which has continuous amplitudes. Okay, so this is a discrete time random process which is evaluated at discrete times, but it has continuous amplitudes because W's are Gaussian. Okay, something we've done before or looked at before. Now, what we're interested in here is, so let's say first of all, what is the mean function? So that's just the expected value of x of n. So what is this going to be equal to? Jimosin.
So the sum of the expectations of Wi.
Yeah. So I can just replace it x of n with the summation of w's, and since expectation is linear, I can have the summation come outside, and this is expected value of wi. But what is the expected value of wi?
So 0.
0, right? So this is simple. This is 0. Right, so the mean function of this is 0. Okay. Now, what about the autocorrelation function? So autocorrelation function for a discrete time random process is defined as this: Rxx evaluated in n1 and n2. So instead of t1, t2, we have n1 and n2 because it's a discrete time process. Okay. So this is defined as the expected value of x evaluated at n1 times x evaluated at n2. Okay. And how do I go about this? This is just expected value of summation I going from 1 to n1 wi times summation I going from 1 to, so actually let me use another variable, not I. So j equals 1 to n2 and wj. Right? Now, how do I go about solving this now? This is equal to what? क्यों माज? What do you think?
सर एक्सपेक्टेशन लीनियर है तो हम सम्स को ऐसे बाहर निकाल सकते हैं.
Okay,
एक्सपेक्टेशन
good. I can take out the sums. I equals 1 to n1 and j equals 1 to n2. And what I have here is expected value of wi times wj. Okay. So then what, Maz?
Because they are independent.
Yeah.
So I think their mean will be they will be zero mean. They will center
Good.
around 0.
Right. So since they're independent and zero mean, what can I conclude? Yimaz?
Okay, that the expected value of the product will also be 0.
Okay, so you're saying wj equals 0. But if this was true, what you're then saying is the autocorrelation function is 0. Is that what you're saying?
I think so. Let me think again.
Okay, good. Nazish, what do you think?
It's sigma square covariance उनका.
Sigma squared. तो लेकिन अगर
Expected value of wi into wj
is sigma squared for all I and j.
yes.
Okay, Mohsin.
सर ये वो सिग्मा स्क्वायर्ड इनटू आइडेंटिटी वाली चीज है ना कि अगर आईआईडी है तो नॉन डायगोनल टर्म्स जो है वो 0 होंगी.
Okay. Right. So Maz, आपने भी खड़ा किया था. You're right, Mohsin.
सर वो यही चीज थी कि जब i is equal to j होगा तब सिग्मा i square आएगा. Other cases में 0 हो जाएगा.
When I is not equal to j, that's when the expected value of this product is 0, because I is not equal to j means that wi and wj are different random variables. And if they're different random variables, the expectation of the product is equal to 0 because they're independent and 0 mean, and so therefore this is true. Okay? I mean, they can. The expectation of the product is the product of expectations when they're independent, and since they're 0 mean, the product is 0. However, when I equals j, then this is expected value of wi squared, which is nothing but sigma squared. Okay? So this expected value of wi times wj is actually equal to what is equal to sigma squared times delta of I minus j, right? So the Kronecker delta function, right? So this is I equals 1 to n1, j equals 1 to n2 times sigma squared delta I minus j. What is this equal to? So what is this summation? So summation क्या बनेगी? Okay, I'm saying this is simple signal stuff. It turns out this is going to be equal to minimum of n1 and n2 times sigma squared. Right, the minimum value. So if n1 was equal to n2, should have been very clear that this would have been equal to n times sigma squared. But since n1 may not be equal to n2, okay, so in that case, this is just the minimum of n1 and 2 times sigma squared. Okay. Questions here before we take a short break? Okay. So the next topic or the next tool for characterizing random processes is quite related to the autocorrelation function, except that autocorrelation ke saath there's one thing that we did when we talked about pairs of random variables, right? Very, very related to correlations. Can somebody remind me that? कि अगर हम बाई सब्ट्रैक्ट कर देते थे तो फिर क्या होता था? Covariance, good, right? So very related to correlations are covariances. The only difference being that when computing the covariances, all you do is subtract the biases, okay? And just following the same set of principles, another tool to characterize random processes is the autocovariance functions. And the definition is as follows. So we use C to denote it, x evaluated at time t1 and t2. What do you think the definition is going to be? Let's see if you can guess what the definition should be. Timosen.
So the autocorrelation minus mu x at t1 and then mu x at t2.
Okay, good. Right. So this is just, remember, if you just relate the random process to random variables and just realize that the random process sampled at t1 is nothing but a random variable, that's enough for you to be able to extend those ideas here as well, right? So x of t1 is a random variable, and the mean for that random variable is mu x of t1, right? So this is what it is, right? So that's what I meant by subtracting the bias times x of t2, which is another random variable, minus the mean of this random variable, which is mu x of t2. Right? And you can very, very easily derive that this is equal to Rx of T1, T2 minus the product of the means. Just like we did with the pairs of random variables, right? So the ideas are exactly similar. The only difference being what? That now we have this arguments T1 and T2 there, right? So for a fixed T1, T2, there's nothing but constants. Okay, but as such, you need to evaluate this for all pairs of T1s and T2s. Okay, so this is the auto covariance function, right? So let me do an example here. So let's say you have this random process, which is x of t equals small s of t plus n of t, where this s of t is actually a deterministic signal. And this n of t is random and it's actually noise. I mean, the n basically refers to the fact that this is noise. And this is actually any practical measurement of any signal that you get is going to correspond to this model, where there's something, a deterministic signal that perhaps that you're trying to measure. Okay? But what you actually end up measuring is that deterministic signal plus some noise signal, right? And that noise signal is a random signal, right? So you can never be sure that x of t is actually going to be equal to s of t. X of t is always some as a noisy version of the signal of interest. Okay. Now, given this model, what we are interested in is determining, for example, the covariance of x. Right. Let's say you're asked to derive the covariance of x. Before that, let me just tell you that the expected value of n of t is 0, and that's the most typical case, by the way, in practical measurement systems, right? So whenever when you're measuring, the noise is always 0 mean, right? If it's not 0 mean, you can just subtract the bias anyway from your measurements, right? So it makes sense to always consider the noise to be 0 mean. Okay, if noise is 0 mean, what can you say about the expected value of x or the mean function of x? What do you think it's going to be? Ji Shaila or Isha?
Sir, S of t पर dependent होगी only.
Okay, S of t पे dependent होगी किस तरह?
We will have expected value of S of t plus N of t.
Yeah, what is the expected value of, so this is okay.
That
So
will
this is expected
simply
value of S of t plus N of t. What is this equal to?
expected value of S of t.
Okay, expected value of S of t. What is this equal to?
Sir, जो signal होगा.
Right, so this is equal to S of t. Why? Because Jim was in.
Yeah.
Yes, the signal is deterministic, right? So that's what I wrote up about. S of t is deterministic, so the expectation is that thing itself. Okay, so the expected value, the average value of this of the process X is just equal to the signal of interest. Okay, that's what the average value is. What about C, or the covariance of X evaluated at T1 and T2? So this is equal to expected value of X of t minus mu X of T1. So this is T1 times X of T2 minus mu X of T2. Right? So what is this equal to? I mean, how do I go about this? So there's an easy way of doing it. There's a hard way of doing it. The hard way of doing it is expanding these brackets, right? And you say this is now composed of 4 terms, right? And you compute the expectation of each one of those terms separately. There's an easy way of doing it. Jimaz?
Sir, ये X of T1, X of T minus U X of T is basically N of T.
Good.
So,
right. So this is just
simple.
equal to expected value of N of T1 times expected value of N of T2. And what is this equal to as some function? Jimaz?
Sir, ये autocorrelation function है N of T का.
So this is the order
और N
of T of N, which is also the covariance function, autocovariance function of the noise. Right? Why? Because N is 0 mean. Because N is 0 mean. Okay. Achha, by the way, given the autocovariance function, can you determine the variance of X? So, given Cx of T1, T2, can we determine the variance of X of T, which, by the way, will be a function of time, right? As a function of time. What do you think? Can we or can we not? What do I mean by variance? Is expected value of X of T minus mu X of T whole squared. Can I do that? I mean, can the covariance function give me the variance? Jimaz?
Sir, अगर हम same time compute करें covariance, so I think that will give us the variance.
Right. So this is equal to. So this is actually equal to Cxx evaluated at the same time T and T. Right, and I just vary T, and that will give me the variance at each and every one of the points. ठीक है, at each and every one of the time samples. Okay. All right. Any questions here? All right. So the last thing we want to do, most likely, is something called stationary processes. And in some form or the other, by the way, these are all concepts that you would have done already in some course or the other. I'm assuming in your undergraduate studies, communications type का कोई course लिया होगा. Did you talk about processes and stationary processes? Just want to find out. जी मोहसिन, go ahead.
सर मैंने डिजिटल कम्युनिकेशन प्रिंसिपल्स में पहली बार देखा था ये.
कॉम सिस्टम्स में नहीं देखा था.
Sir, that I don't remember.
Okay. How about somebody else? Nazish?
मुझे याद भी नहीं.
Okay, because I've seen some notes इसमें they do talk about this. SFT plus NFT type चीजें मैंने बहुत देखी थी. But nevertheless, so let's review this. Strict and stationary processes. Achha, as a side note, I think I may have talked about this in one of my early classes as well. You know, a shortcut of way of remembering, there are two types of stationary, right? With stationary with an A and stationary with an E. Right? How do you remember कि A कहाँ लगना है और E कहाँ से लगना है? Right? The way I remember that is what my mother taught me when I was a little kid, right? So she told me our stationery is pen and pencil. Exactly. Yeah, so Isha, maybe I've mentioned this earlier, right? So stationery is pen and pencil, so it has an E, so that's a way of remembering it. Okay, so the other one must be with an A. Okay, anyway, but that's besides the point. So strict and stationary. What is meant by a strict and stationary process? We say that process is strict and stationary if the statistics are invariant to time shifts. What I mean by that is that if I give you any nth order PDF of that process, right? So let's assume that we're talking about a continuous time process, which has continuous amplitudes, okay? So the nth order PDF is something which looks like this. This is x1, x2, all the way up to xn, evaluated at n time instances, any arbitrary time instances, t1, t2, all the way up to tn. Right, so this is the nth order PDF for any integer n which is greater than or equal to 1. Right, so I can describe nth order PDF for any process, and that's actually, this is what you need for any n is greater than or equal to 1. This is what you need to completely characterize a random process, all nth order PDFs. Okay, now if this turns out to be equal to a function which looks exactly the same n-dimensional function when evaluated at a time displacement t1 plus tau, t2 plus tau, all the way up to tn plus tau, right? For a fixed tau. What that means is if I pick time instances t1 through tn and evaluate the nth order PDF for this random process, the process is going to be strict and stationary. If this PDF stays the same, even if I say the same, if I shift those time instances all the way, all of them, slide them or translate them by tau seconds, either to the right or to the left, doesn't matter. Okay? What that means is as long as the inter-time distances or the inter-durations stay the same, that's what the PDF is going to be a function of. Okay? So once again, if for example, ये T1 था, ये T2 था, or ये T3 था, let's say n equals 3, right? And this is x of T1 and x of T2, and this is x of T3. The third order PDF, for example, for this random process, if it stays the same for time instances which are shifted by tau, in other words, this is x of T1 plus tau, x of T2 plus tau, and x of T3 plus tau, right? So this is now evaluated at T1 plus tau, T2 plus tau, and T3 plus tau, right? If all the time instances are just translated by a constant amount, and if the PDF stays the same, then that process is going to be said to be a strict sense stationary process. And this condition needs to be satisfied for all n, not just one, not just two, not just three, for each and every one of the n's. Okay? If that condition is satisfied, that process is said to be a strict sense stationary process. Okay? That's the definition of a strict sense stationary process. Okay? Any questions here? Now, in practice, strict sense stationary processes are not only hard to come by, but also they're hard to verify. If I give you a process and ask you, is this strict sense stationary or not? It's very hard to verify whether it is or not, because if in order to completely verify that it is, you will actually need to compute the nth order PDFs, right? So for all n's, and then you need to verify if I translate it, does the PDF stay the same? Does the n-dimensional function stay the same or not? Okay, that's hard to verify in practice. Okay, so that's why we don't very often deal with strict sense stationary processes or the analysis of it in practice, right? So in general, the conclusion I can say is, okay, it is difficult to show strict sense stationarity. And because of that, in many practical scenarios, so we define a looser form of stationarity. Loser भी दो किस्म के lose होते हैं, with a single O and with a double O. Right? So it's a looser form of stationarity. And can somebody tell me what that looser form of stationarity is? So they're called wide sense stationary processes. Okay, so what are wide sense stationary processes? So, I'll answer Shaila's and Isha's question. I'm sure Isha has asked this. So, after the class ends. Ji Mohsin.
So, mean and autocorrelation function are time invariant.
Yeah. So, is this something you remember from digital com?
Yes, sir.
Okay. Not from com systems?
No, sir.
Okay. So, okay. A random process is said to be wide sense stationary if the following two conditions are satisfied. And what are those conditions? The first condition is that the mean function must be invariant to time shifts. Invariant to time shifts. And the second condition is, that the autocorrelation function is also invariant to time shifts, right? So what that means is, if I just look at the condition one, what that says, if I have mu x of t, it should stay invariant to time shifts. That what that means is that this must be equal to mu x of t plus tau. Any shift that I have in time, the function should stay the same. And this should be true for all time t and for all tau, right? What's the only way this could happen? What is the only way that mu x of t equals mu x of t plus tau for all tau and for all t? नहीं, एक जगह पे मैं सैंपल करता हूं अगर सिग्नल को, तो वो सिग्नल जहां मर्जी इसकी मैं डिले दे दूं, सिग्नल वही रहना चाहिए. What is that only kind of a signal or a function that satisfies this property? Somebody other than Mohsen. Good, Josefa. Right? So that signal must have a constant value. I mean, that's the only way this condition is going to be satisfied, right? So this implies that the mean function for a White's and stationary process must be not a function of time really. It should be a constant, right? It should be a constant value, a DC value, if you will. A value that does not change with time. Okay, so a White's and stationary process satisfies this property. Okay, and the second condition, if I look at the second condition, what that says is okay, Rx x t1 t2, this should be independent or should be invariant to time shift. So in other words, if I value this function now at t1 plus tau and t2 plus tau, this equality should be satisfied for all t1, for all t2, and for all tau. Okay? What does this mean now? Okay, what the function is actually a function of is the difference between t1 and t2. That's the only way this condition is going to be satisfied. Okay, if this thing here has to be equal to this thing here, right? They're equal only when the x t1 and t2 is a function of t2 minus t1, right? Is a difference between t2 and t1, right? And that's why for White's and stationary process, we say that we only use a single variable to characterize the autocorrelation function, and that single variable is tau, which actually represents कि आप दो time instance पे sample तो कर रहे थे, but what actually it's a function of is what the separation in the time is. Okay, that's what we use for White's and stationary process. Okay, so this is what we use for White's and stationary process. This is what we use for White's and stationary processes. Okay, now can we say something about Josefa?
Sir, I didn't get the last thing that you mentioned about the difference in the two.
Okay, so the difference. So the only way you see the Rxs of T1 and T2 is going to be equal to Rxs of T1 plus tau and T2 plus tau, no matter what tau is, no matter what T1 and T2 is. The only way this is going to be satisfied is if the actual signal is a function of the difference between T1 and T2. Why? Because यहाँ पे difference क्या रहता है? T2 minus T1, right? So difference is T2 minus T1 here. What about the difference here? Here, difference is in the same case is still T2 minus T1. Right? In both cases, the difference stays the same. And the functions are same. It's covered that it must be a function of the difference only.
Oh, okay.
Because that's what remains constant on both sides.
Okay, sir.
Okay?
Nice. Thank you.
Right. Was there another question? No. All right. Okay. So this is a White's stationary process. Should I do So I'm going to skip an example. Let me just spend the last few minutes on. Acha, one point I forgot. What is the relationship between white sense stationary processes and strict sense stationary processes? Can you take a guess? So if I tell you that a process is strict sense stationary, is that guaranteed to be white sense stationary as well? Kyung Ghazi, what do you think?
No.
No?
If it's strict sense stationary process, we can't really say it's WSS.
Okay. Why do you think that is? So strict sense stationary process में क्या होता है?
Okay. जो आपकी nth आपने जो अपनी nth order define
Yeah.
की होती है चीज वो हर tau के लिए satisfy होती है.
Good, right? So that means that for a strict sense stationary process, the first order PDF should be invariant to time shifts, and the second order PDF should also be invariant to time shifts, and so on and so forth. The third as well, the fourth order as well, and so on and so forth. Okay? Right? What is the mean function a function of? Isn't that a function of the first order PDF? Ghazi?
Yes, it is of the first order.
So the main function is a function of the first order PDF. So if the first order PDF is invariant to time shifts, that means the main function should also be invariant to time shifts. Okay. And a similar argument I can make about the second order PDF as well, because the autocovariance function is a function of the second order PDF. And since the second order PDF is invariant to time shifts, the autocorrelation function must also be invariant to time shifts as well. And because of that argument, I can conclude that strict sense stationary processes are guaranteed to be white sense stationary processes, right? So therefore, one is a subset of the other. Okay, so white sense stationary processes are a larger classes of processes, right? And amongst them is white sense stationary, strict sense stationary, which is a smaller class. Okay, so all strict sense stationary processes are actually guaranteed to be white sense stationary processes, but not the other way around. Giuseppe?
Sir, I'm just confused that we define that in a white sense stationary process, the mean stays the same regardless of wherever we are sampling the.
Yeah.
So, but that isn't the case in strict sense stationary processes. So, how do we say
Okay,
that
why is it? Why do you think is not the case there?
So because when defining a white sense stationary process, we defined it to be like a constant signal, basically a DC value. But
so Josefa, see here. So I'm going to make some notes here, right? So this is if I'm just going to consider the first order PDF for a strict sense stationary process, okay, and that is fx of x as a function of time. Okay, that's the first order PDF. And I say okay, for a strict sense stationary process, this must be equal to this thing here, x and t plus tau for all t and for all tau. Right?
Yes, sir.
What does this imply? The only way this can happen is if this is going to be satisfied for all t and for all tau, that means this first order PDF ends up not being function of time. Just like the mean function not being ended up not a function of time. वही argument आपने ही answer दिया था, ठीक है, constant value वाली. यहाँ पे भी argument apply होता है, right? This implies that fx of x is actually equal to just fx of x. It's not a function of time. Because no matter where you sample it at, it must stay the same. Right? Josefa, you get the point?
Yes, sir.
If the first order PDF is not a function of time, what can you say about the mean function?
That won't be a function of time too.
That will not be a function of time either, right? So I mean, I'm doing some analysis here, right? So this must be fx of x dx, and I clearly see that this is not a function of time. So therefore, that mu x of t is going to be equal to mu x. Right, just a little bit on the side, right? Just to indicate here, a strict stationary process in which the first order PDF is invariant to time shifts implies that the mean is also going to be invariant to time shifts, which essentially is a constant value. And you can use the same argument for the second order PDF as well. Okay. So conclusion here is, okay, all strict sense stationary processes are wide sense stationary, but not vice versa. Okay, so we've run out of time. So there's one other topic that I wanted to do. I'm going to skip that, and I'm going to stop here. For any questions? Any questions before we end? Jimosin.
So for most things that we've studied, we've extended it to a collection of n random variables.
Yeah.
So in the case of correlation and covariance, do we only use a pair of random variables?
Excellent point, Mohsin. Yes, we only stick with pairs. Okay, so covariance and correlations are applicable to pairs of random variables only. Right? Off the top of my head, I am not aware of if they're extendable to, or how they're extended to more than pairs. Something I would have to look up. Okay, but that's a good point. If you find out something, let me know.
Yes, sir.
Right. Any other questions? So I leave you off with just one exercise, if you will, or proof, if you will, and say, Kiji, for a 6-9 stationary process, what does this represent? What is the meaning of this? And you will find here this is the average power in the process. How? Give it a little bit of thought. You may be able to find this in the book as well. Okay, so there's a very, very practical implications of the things that we've done. Which unfortunately we don't have a lot of time, or actually no time at all, to go into. Okay, so I'm going to stop here.